Hey YouTube, I've put together a quick video on RC power basics, and the reason for this video is because I am constantly stunned at how much lack of basic understanding there is out there on batteries and power development and the relationship of the prop to the equation when it comes to the airplane. So I've spent a lot of time in the last couple of years really kind of studying and learning and trying to teach myself and watching tons of videos and other material out there. So I decided I just wanted to put my own spin together on how I go through the process. So this isn't it's not a flight video. This is kind of a presentation oriented video, but mainly it's designed to help put power basics together and give you some good rules of thumb you can use when you're thinking about how to configure an airplane, what type of batteries you need, and that type of thing. You know, how to configure the power for the plane. So with that, a quick little refresher. I think most people have probably seen something like this, and if you're watching this video, you've probably have definitely seen something like this. But just a quick little refresher that three of the key ingredients when it comes to making power on an electric plane are volts, amps, and watts. So when I think about wattage, I think about light bulbs. That's the easiest correlation I could make when I first started getting into this. And that's that watts, light bulbs, the more watts light bulb has, the brighter it is, right? Same thing with a motor. The more watts that you're producing, the more power that motor has. Voltage represents pressure, so that's how much pressure the system is pushing current through the system, and current is represented by amperage. That's the next one. So current or amperage are used interchangeably. That represents the flow of power through the electrical system that we're working with. And there's a triangle that's well used out there. It's the electrician's triangle. Basically, volts times amps equals watts. So you can figure things out with this simple formula. Batteries, for example, if you have a 12-volt battery and you have 10 amps, that means you've got 120 watts. And then likewise, you can do division and say, well, if I know how many watts I have and I know how many volts I have, then I can figure out what my amps are going to be. So we'll get into a couple of examples in the next page, but the idea is that you can reverse engineer things too. So watts divided by volts is amps, and also watts divided by amps is volts. Okay, so simple formula. Just keep this in mind as we progress through the rest of the material. And this watts, volts, and amps triangle I use it all the time when I'm thinking about power and batteries and ESCs and motors and propellers. I mean, this just comes into the equation all the time when you fly electric. Okay, the other thing I wanted to do a quick little review on is this watts per pound guideline that eFlight put out. I stumbled onto this a long time ago, a couple years ago, I should say, and it's really good. I know that if you're really heavy into flying and you're a real geek about it, you may have a completely different point of view. But if you're new and you're not exactly sure where to start out, this chart is a really decent place to get an understanding of where you need to configure your airplane to fly. So for me, a lot of my planes that I fly, I like this 110 to 130 watts per pound number for the type of flying that I like to do. But what this chart is showing you is how many watts you need per pound of airplane to get the flying characteristic listed. So let's go through a couple of them. First off, forget about 50 to 70. I mean, unless you're flying inside like a gymnasium or something, I don't think 50 to 70 is good for much. I would start minimally at 70 to 90. But it's 70 to 90 watts per pound. Let's just say, for example, you have a 1-pound aircraft. A 1-pound aircraft, you probably want somewhere between 70 and 90 watts if that aircraft is a trainer or a slow flying scale model. If that aircraft is a sport plane or a faster flying scale model, you want to come in somewhere between 90 and 110 watts per pound. So if you have a 1-pound airplane, you're 110 watts. That's what you need. If you're a 2-pound airplane, you need 220 watts, right? So it's real simple guideline on how to at least start zeroing in on where you need to be. And a lot of times, depending on what you're building and the type of flying you like to do, it almost seems like black magic sometimes. So having this chart is a good reference point. And I'm really happy E-flite put it out there, but it's a good reference point to kind of get you started. And once you get started, these guidelines, you can adjust. You can say, well, I want mine to make more power or less power. I don't need that much power for this type of plane. So you can make your adjustments as you see fit. But it's a good reference and a place to start. So for the example, we're going to use 130 watts per pound. That's just a number that I happen to like. I like the way my airplanes feel when I'm making that kind of power. And by the way, that's not good for 3D. So if you're talking about 3D, that's a whole nother animal altogether. And in that model, since I'm not experienced at 3D, I'll leave it to other people to decide where to go. But the chart recommends 200 watts plus, so 200 watts per pound plus. And I believe that because my planes, I don't really design them for that type of power. But if I were going to be doing what they'd call unlimited performance and unlimited vertical, I might be thinking about something up in that higher end. Okay, next thing you got to do is figure out what size prop do you need. And it maybe seems a little counterintuitive, and I had a hard time with this when I first got started as well, but the prop size really matters because you got to think about things like prop clearance. You definitely want, obviously you can't have a prop that's hitting the ground. If you have a tail dragger and you get up on the mains, you don't want your prop striking the asphalt. If you've got a nose wheel airplane, you don't want just a couple millimeters of clearance because as you do an approach, you might end up chipping your prop. You just need clearance. So the airframe kind of dictates the prop size. So that's the one thing you can't really change is what's the relationship between the nose of the plane or the tail of the plane or the airframe of the plane and the dimension of the propeller, at least the diameter. So you kind of have to start with this because it's a physical constraint. So the things to remember about making selections regarding your propeller is that your amperage changes with your prop diameter. So the bigger your prop diameter, the more amps you draw. The more prop pitch you have, the more amps you draw. The more blades you add, the more amps you draw. Now this particular picture shows just a bunch of 2-bladed props, but if you have 3 or 4-bladed props in the equation, say you're flying a warbird, you're going to draw more amps. Now, in general, and this isn't completely scientific, but it's a general rule of thumb. So yes, I know that it's not always the same and that the diameter of the prop will have an influence on how close these trade-offs are. But in general, a rule of thumb is you can trade things like diameter for pitch. So for example, let's say you started with a 10-inch prop. Let's say we'll call it a 10-6 prop, and you say, well, the 10-inch prop is too big, so I need to go down to a 9, but I want to keep the wattage the same. I want to keep the power level the same. You could go to a 9-7, so you could take a 10-6 and drop it down 1 inch and increase it 1 degree of pitch, so you could go from a 10-6 to a 9-7. You can also trade an inch of diameter for a blade. So if you're flying a 2-bladed prop and you decide I'd like to have a 3-bladed prop, you could go from say a 10-inch diameter 2-blade to a 9-inch diameter 3-blade. And then the same for pitch. You can trade a degree of pitch for a blade as well. So let's say that you're flying a 3-blade, but you want the plane to go faster. So let's say you've got a 10-5 3-blade prop. You could go to a 10-6 2-blade prop. So you give up a blade, but you increase your pitch. So in the example we're going to use, we'll start with a prop diameter of 10 inch. We'll just say my particular airplane requires a 10-inch prop. And the idea when you're building your power system is start with a prop diameter that fits your plane. Okay. Now again, I just want to say that in my experiments with props and watt meters and testing, these trade-offs aren't perfect across the board. They're not uniform. I'm not suggesting that every time you trade 1 inch of diameter for 1 degree of pitch, that your watts will stay exactly the same or your amp draw will stay exactly the same. They're just general guidelines. All right, that's it. All right, so back to our volts, amps, and watts, because we're going to start stitching this together, okay? And I wanted to put one last little item up on the screen so you can see the relationship between volts and amps, and this has to do with battery selection, okay? So we said volts times amps equals watts. So if I have 10 volts and 10 amps, that's 100 watts. All right. I can flip that around and say, well, if I have 100 watts, I can divide that by 10 volts and get 10 amps. I can also take 100 watts and divide it by 20 volts and only use 5 amps. You see what happened there? My amp demand decreased because I raised my voltage. So I went from 10 volts to 20 volts. This would be similar to, say, a 3-cell pack and a 5-cell pack. And when just by switching the battery alone, my amp draw cut in half. And that'll go to battery capacity and the ESC required and other things. But I just wanted to put this out there so you could see an example of what happens when you change your voltage. So keep in mind, the more volts you use, typically the less prop you're going to use. Less diameter, fewer blades, less pitch. So for a given airplane, if you want to maintain a certain amp draw or a certain wattage level and you change the volts, then generally you have to prop down a little bit. You're going to use a smaller diameter prop or fewer blades or a little less pitch. So when I think about the idea of going from say a 3-cell to a 4-cell pack, I would say, okay, well, if I'm a 3-cell pack, I might use a 9-inch prop. If I'm going to a 4-cell, I'm going to use an 8-inch prop if I want everything else to stay the same. So that's a general rule of thumb. As you add voltage, if you want everything else to stay the same, you have to prop down a little bit. Use a smaller diameter, fewer blades, or smaller pitch. All right, so we'll use a real-life example. This is very similar to a plane I just completed. It's a 7.5-pound airplane. Remember that 130 watts per pound number I like to shoot for? So 7.5 pounds times 130 watts per pound means I need 975 watts. All right, that's what I need my motor to deliver. Now, if I'll use my formula, 20 volts. In my case, I have a 5-cell battery that I want to use in this particular configuration. I know that 5-cell battery will fit the battery compartment in the airplane. So I'll take 975 watts, which is what I want for this particular design, and I'm going to divide that by the 5-cell pack that I plan on using in this design, and that leaves me with 48.75 amps is the required amount of amperage I need to be able to deliver. So now I've got something I can work with. I know what my amp requirements are. Now I can start designing the system. Okay, now let's talk a little bit about C, because to me, this is one of the biggest travesties out there. It's amazing to me how many people fly who have no idea what all this stuff means. They just, it's almost like they're just throwing darts at a dartboard. But let's talk about C for a minute. All right, because it's used quite a bit, and you really kind of need to understand it. So C is the rate of charge or discharge relative to capacity of the battery over an hour. So that's the kind of, go look it up. That's kind of like the basic textbook definition. But let's get into what it all means, okay? So in this battery pack, you'll see that, I got to make a point first. Higher C rates mean the pack is more tolerant to higher charge and or discharge rates. Now, if you look at this particular pack, you can see here that this guy is listed as a 40 to 50 C discharge pack. Okay, there are other 2200 milliamp hour packs that I've used that are 20 to 25 C. So if you look at the statement that I made here, higher C rates are more tolerant to higher charge or discharge amperage. What that means is if I'm going to run, say, 60 amps, okay, I can probably do it on a 25C pack, but that's really pushing it. 60 amps on this particular battery is nothing, because what this pack or what these designators tell me is I've got a range of 40 to 50 C of discharge capacity against 2.2 amps. So that basically means I take 2.2 times the C rating, and I'll even use the low end, That gives me
88 amps of discharge.
So this is another area of confusion. This 2200 milliamp hours that you see, that's a reference to capacity. So in order to figure out what that means in terms of amps, you simply move the decimal place over three places. Okay, so a 2200 milliamp hour pack is 2.2 amp hours, or simply 2.2 amps. All right, so now we can take that 2.2 number and use it to figure out other things. So what other things does this apply to on the battery? So in this example of a 2200 milliamp hour pack, or 2.2 amp pack, and a 40 to 50 C discharge rate, that means this battery pack is comfortable delivering between 88 and 110 amperage discharge. Okay, 50 C is probably the high side or burst rate, and then 40 C right here is probably the constant rate. That's the way I would treat this battery, even though that's not exactly how it's labeled. So what that tells me is I can run this thing all day long at 88 amps, and I can burst to 110 amps for about 30 seconds without really damaging the battery. Now, here's why this becomes important, because I hear guys all the time say, oh, well, you got to have a 100C discharge pack. And they're taking that 100C discharge pack on a 30 or 40 amp ESC. So why? I don't understand. Why do you need a pack that's capable of a constant discharge running an ESC that can only deliver 40 or maybe 50 amps, right? You're going to burst for a little bit so you can run 50 amps. So why on earth do you need a 100 amp pack to run an ESC that maxes out at 40 amps? It doesn't make sense. Now, one thing I will say that does make sense to me is that the higher the discharge rate capacity, the higher the C rating on discharge, the less voltage sag you wind up with. So if you have a high discharge C pack, you can tend to run it at higher power levels with less voltage sag over a period of time than a lower C pack. So if that's important to you, if you're into racing or maintaining a certain speed for a given amount of time, then I can see why that might be important. But regarding the math says you only need to really put a battery pack in with a discharge rate that is north of what your ESC can deliver. So just keep that in mind. So that's why I asked this question. What's the max amperage draw of your motor prop combination? Once you know what that is, you can design or choose a battery that matches the max amperage draw of your motor and prop combo. And one last thing I'll say about this too is that overhead is important. And what I mean by overhead is I never design an electrical system. If I do the math and say, okay, I need to be able to deliver 39.8 amps, I'm not going to pick a 40 amp ESC, because what that means is that at peak, I have no overhead. I have no room for burst energy, and I'm really going to be pushing the electronics to their limit. So I tend to design everything I do with a little bit of overhead, meaning the ESC gets a little more capacity, the battery gets a little more capacity, the motor can deliver a little more capacity than what I need. Okay, so now let's put it all together. We'll take all that information we just talked about and stick it together into a formula that works. So I mentioned a couple pages back that in our example, I'm going to say on this particular airplane design, I need a 10-inch prop. And the 7 there is a reference to the pitch, and I pulled that off of a motor chart that I had already seen. So I was already familiar with it, so I'm using a 10-inch by 7 pitch prop. We know we need 975 watts. We figured that out based on the weight of the airplane and the E-Flight chart that I put up. I'm using a 5S battery, so I knew that already. I have that battery, so I'm designing around that a little bit. I'm using that as a consideration for my electric design. If I had a 6S battery that I wanted to use, I might change this formula a little bit, but I don't. I'm using a 5S pack. I know that I need to create, based on these rules, 975 divided by 20 amps, I get 48.75. First thing I'm going to do is round that, because they don't make a 49 amp ESC, so I'm going to choose a 50 amp ESC. But remember what I told you about overhead. This is where that becomes important. 10% is a good number. So I'm not going to select the 50 amp ESC. I want 10% overhead, which means 60 amp is the ESC I would choose for this setup. And then I just know based on personal experience that means I'm going to wind up with about a 42 millimeter motor that runs about 800 kV. Now, the point of all this is now you have what you need. You know what your prop size is, you know what your wattage is, you know what your voltage is, and you know what your amp draw is. You know what all those things are. Now you can just go shop and look at the specs. And good motor companies will put data points out there telling you with a given prop size, a given voltage, here's what kind of wattage you should expect to draw, and here's the amperage that we saw when we tested the motor given those parameters. So I just happen to know that, you know, for this particular layout, this would be probably a pretty good motor selection for this type of plane given the parameters I've established. And then regarding the battery, I just wanted to take an example and say, okay, if I've got a 3300 milliamp hour pack, I need to have at least an 18C discharge rate. Well, how did I figure that out? I took my 60 amp ESC, my 60 amp limit on my ESC, that's as high as my ESC could go, right? 60 amps. I divided it by 3.3, that's 3.3 milliamps, and that tells me I need an 18C discharge rate. Remember, here's the formula again. You take your amperage of the battery. In this case, it's a 2200 milliamp hour pack. I just moved my decimal over 3 places. That tells me 2.2 amps. And I multiply that times the discharge rate. So in this case, this pack is good for 110 bursts and 88. On the putting it all together slide, all I did was reverse that. I said, well, I've got a 60 amp ESC and I've got a 3.3 milliamp a 3.3 amp hour battery, or 3300 milliamp hour battery. So it's 3.3 amps, 60 amps divided by 3.3 equals 18C. That's the discharge rate I need to have minimally for this configuration. And all of my batteries in that voltage range are well north of 18C. They're all going to be, 30 or 40 C packs. So I know my battery will be able to tolerate that motor and prop design as well. All right, the last thing I wanted to cover is just a quick little, it's this kind of a more advanced thing, but there might be cases where you say, well, look, I don't want to run, well, I'll give you a great example. I have an airplane that flies a 4400 four-cell, but I don't have any 4400 four-cells. So what I do is I take two 2200 four-cells and I put them in parallel. And what that does is it gives me the capacity and the voltage that I need to fly that airplane without having to go out and buy a dedicated battery pack. And I can still use those 2200 four-cells on other airplanes that I have. So learning how to use batteries in series and parallel can give you a lot of flexibility in terms of the types of batteries you keep in your stash and what you might be able to do to put something together for testing or for flying. So if you decided you wanted, say, a 6-cell design or 6-cell battery setup, you could take two 3S packs and wire them in series, and there you go. You got a 6-cell battery. So here's some basic rules about flying in series or wiring batteries in series versus parallel. Okay? The example I'm going to use is two 2200 milliamp hour 3-cell packs. Those are the good old fashioned common 2200 milliamp hour packs. All right, so if I took that setup and put it in series, here's what I'd wind up with. I'd get 2200 milliamp hours worth of capacity at 24 volts. So when you wire batteries in series, remember this. Your voltage changes, your amperage or capacity stays the same. Different voltages are okay, and you want to use the same capacity only, because if you have say a 2200 and a 3300, what'll wind up happening is your 2200 will discharge first, and you can over discharge the pack. So not a good idea to mix capacities when you wire in series, but you can mix voltage. Voltage in series is additive. So if you have a 12 volt pack and a 6 volt pack, you'll have 18 volts if you wire them in series. All right, in parallel, it's basically the inverse. So in parallel, your voltage stays the same. It doesn't change. So when you put two batteries in parallel, if you start out with a 3-cell packs, you'll get 12 volts, but your capacity doubles to 4,400 milliamps. So your voltage stays the same. Your amperage capacity is what changes. It went, instead of being a 2,200 milliamp hour pack, you have a 4,400 milliamp hours worth of capacity. You can only use the same voltage. You do not want to wire things together in parallel unless they're the same voltage. And you can use different capacities. You can take a 1,000 milliamp hour 3-cell and a 2,200 milliamp hour 3-cell and wire them in parallel, and they'll discharge simultaneously down to 80 or 25%. It's just the way it works. So that's it. That's the in the end of the material. I hope it's been useful for you. I put it together basically just as a reference, and there's so much more information out there. I mean, I don't know how many minutes I've been talking, but in this amount of time, all I did was cover the bare basics. But it's good reference material. I hope that it can help some of you guys out there who aren't sure what all the C business means and what the parallel versus series stuff means, or where do you start on configuring your motor and prop. I hope this kind of helps you work your way through that. So, bookmark it, use it for reference. And if you like the material, please engage in some conversation. Comments help. Thumbs up, thumbs down if you didn't like it. Any interaction helps with my videos getting better placement when other folks are looking for this type of content. All right, hope you enjoyed the video. Thanks for watching. Take care.